Here we will introduce some new tools and continue to work with some tools we have already used. To get started, we read in our packages. We are introducing a new package here. This is GG Extra. You will have to install it before reading it into your library. And we will work with the same ROA data that we've worked with in the past. These are the same functions we've already used. So miss is removing missing values. Outlier is removing outliers or changing outliers so that the extremes are moved into the first and the 99th percentiles of the distribution. We will introduce two new functions here. This first one is a ranking function. Let me just describe it a little bit and then you can work through it if you'd like. X is the column that we're inputting into the function. In groups is the number of groups that we want to rank the column into. So if we want to rank it into 100 groups, so that would be percentiles, we would put 100 here. If we want to do 2 groups, we'd put 2 here. That's what this does. And then you don't need to worry about how the function is created too much, but I want to just briefly tell you about it. So we're taking this column X and we're ranking that. So ranking would be 1 to however many observations there are. So if we used this whole data set, that ranking function would go 1 to 35,154. And the method tells the ranking function what to do with tie values when 2 rows have the same value. We divide by how many rows there are in X, so length of the column is the same as number of rows. So how long is the column? So in this case it would be 35154. So when you divide by the total and it's ranked, this gives you a percent. Then if we multiply by the number of groups, it will change that percent into numbers that look like they're counted from one group to the next. And ceiling rounds up so there are no decimal places. So it's a complicated set of commands here, but it's just trying to rank into different groups. The next one is the standardize function, and there are other ways to do this in R as well, but I think this is fairly straightforward and easy to do. So first, we take a column that is input X. We're going to use that column, subtract the mean of that column, and we need to introduce something new here, na.rm. So na are missing values in R. .rm says remove, so remove missing values before using the mean function. So na.rm equals true, remove missing values before calculating the mean. Dividing by SD is the standard deviation, so the standard deviation of X. So when we create a variable that is X minus the mean divided by the standard deviation, this is creating something called a z-score. When we use a function like this, what it does is make all of the variables have the same mean and the same standard deviation. So it makes it a little bit easier to work with the variables. That will become necessary in the last thing we will do in the video today. All right, so let's go ahead and start doing some of the things we want to do. For this, I'm going to create 2 variables. We've already created ROA at one point, but I want to use ROA from time t and ROA from time t plus 1. So let me walk through each of these steps again so that we remember what we're doing. Start with the data set called temp. That's what we created over here when we imported the data. Create a new data frame, temp2. Continue to work with that using this pipe function. Arrange is sorting, so I am sorting by the company and the year. So using the distinct function, it will remove duplicate values. So if we have more than one row for a particular company and fiscal year, then it will delete the second or third or however many of those there are. And .keepAll says keep other columns as well. If not, it would only keep the 2 columns that we put in the distinct function. Then we are going to group by company. The reason we are doing this is because in the mutate function we will have a lag and a lead, and moving up or down rows in the data frame can cause problems if we don't tell R that we are working with unique types of observations. So here we have net income from year T divided by the lag of 1 year total assets. So by lag, it means move up 1 row because we are sorted by fiscal year. We are also going to create here the ROA from the following year. So if we're in 2019, we're going to calculate the ROA for 2020. So notice we have the same things in here. This is net income and total assets, but instead of lagging total assets, we're going to use this year's total assets and next year's net income. So lead moves down a row, so we will move down a row, grab that net income, divide by this year's total assets. This underscore LD1, this is my way to say LD is lead, so lead 1 row. Lead 1 row meaning 1 year in this data set. Remember, we used group by up here. We need to ungroup because we don't want to run functions unknowingly when things are grouped. Then we've already done this before. We're going to remove missing values from temp2, create a new data frame temp3 from the non-missing values of temp2. Then we're going to remove outliers for these ROA variables. Those work on columns. So using the data frame temp3, we will create a new data frame, which we are also calling temp3. Continuing with the pipe function, notice before we had group by fiscal year when we did the outliers. I'm not doing that here because I just want to show you that sometimes we won't do grouping when we're removing outliers. So this is more for showing you how it works rather than any particular reason. Then we're going to change the columns, that's mutate, create a new column ROA that is using the old column ROA and removing outliers, applying this outlier function. We will do the same thing here with ROA lead 1. At the end, again, ungroup, but notice we weren't grouped anyway, so that's sort of meaningless. So before we get too far, let me run what I've just discussed with you. So we need, notice over here, we don't have them. We need to create our functions, and we will run here up through temp3. Now, just like we did before, we can create a summary of these columns. We will work with ROA and ROA lead 1. This one is the summary of ROA. We saw this before, so it goes from minus 0.66 to positive 0.35. The mean is 0.003. We can do the same thing with ROA lead 1. You would think those should be fairly similar. The difference is that the next year's ROA removes those from our sample that don't have ROA in more than 1 year, so it changes our sample a little bit. And you see the mean is slightly different, so we had ROA of 0.003, here it's 0.0004. The median is fairly close to the same. The min is slightly higher, and the max is slightly lower. Well, we can do other ways to create summary variables. Notice in the summary function that we used, it creates minimum, first quartile, median, mean, third quartile, and max. Well, we don't need to just rely on the summary function, so we can use the average doing mean. You've seen that before. It looks the same here. You can do the standard deviation. That's something that we haven't done, but we just introduced. So here's the standard deviation. The min and the max we've seen in the summary function, but we can calculate those by themselves. A new one that creates these pieces in here that we've used in one of our functions but not used explicitly is this quantile function, and that just tells us at a certain quantile what is the value of ROA. So for the 50th percentile or quantile, ROA is 0.019, and we go up here, that's the same as the median here. Well, we can do something similar to what we have in the summary function. I'm just adding another piece so that we can see what it does, but we have the min here, the max, the first quartile, median, third quartile, and for fun I added in this 10th percentile and 90th percentile. So we can run that and it gives us what we had before, but a few other things. So the reason I'm doing all of this is to help you understand ways to describe the data and some functions available for that. So let's create this in the DPLYR framework. It's the same thing we had up here, but I'm going to create a new column, mean of ROA, standard deviation, minimum, first quartile, median, third quartile, and maximum. And I'll put that in a new data frame, which I'm calling SMRY. For me is summary. So when we view that SMRY, it opens it up and shows you we have the mean, standard deviation, min, quartile 1, median, quartile 3, and max. So something like this is what you will typically see in an academic article that shows you what the data looks like. So when I'm asking for summary statistics or descriptive statistics, that's what those terms mean, something like this. All right, so we have something basic there. Now we want to turn towards correlation. So correlation means how does one variable move as another variable moves. We can do this with graphing techniques, or we can do this with statistical techniques. I'm going to show you some of that here. We've seen this plotting function before. I'm going to save my plot as a plot G. This is the scatter plot from ggplot, and I'm going to use the x variable as ROA and the y variable as ROA lead 1. So in other words, how does ROA in one year correlate with ROA in another year? So we can run this. I've done one more thing here that's slightly different than what we've done before, and that is I've included a vertical line for a reference and a horizontal line for a reference. This intercept here, x-intercept and y-intercept, gives where the line crosses the axis, and here I'm going to have it be at 0, and we can color the line. Here I'm going to do blue, and we can make the line different styles. Here I'm using dash. All right, so I've created this graph. It's not output yet, but it's here saved in this object over here. The ggExtra package allows us to do a little bit kind of a fancier graph. So the marginal graph, this GG marginal, combines a graph that you put in there first, in this case our scatter plot, with something else. And the other thing we're going to combine it with is this histogram for each of the variables, x and y variables. So sometimes this can be a really useful sort of plot. So let me run it so we can plot it. And how you use this function is take a graph object, which we have up here, and then it's going to ask you to add something else to that. That's this type equals histogram. So we run this, takes a minute, and let's open it up so we can see it a little bit easier. So in the middle here, this is the scatter plot, which we would get if we just input G instead of the new function. And notice we have this histogram. This is the histogram for ROA. This is the histogram for ROA T+1. You think, why does that even matter? Well, what it allows us to do is when we see all of these dots here, it allows us to see how much of the distribution is coming from these parts of the dots. Now the dots sort of show that as well, but notice most of the distribution is right in this area for ROA, so we're really looking at this part here of the graph explains most of what's happening with ROA, and similarly with ROA from the next year, you know, somewhere between here and here maybe. So really it's in this area that we're thinking about most of the data. So fun to work with sort of different graphs, and sometimes you can get really useful insights, and sometimes that's necessary. So by correlation, what we're talking about here is how, as we move from low to high for ROA, how does ROA for the following year move as well? Well, here we have something that looks like it could be a positive correlation. The line is sort of going up if we were to draw a line here. More dots down here at the bottom than they are at the top, and more dots up here at the top than they are at the bottom. So if we put a line to the data, we would put something that looks like a positive sloped line. Of Of course, there are dots all over the place, meaning it's not very predictable. So if we have something down here, it could end up sort of anywhere. If we have something up here, it could sort of end up sort of anywhere. So although most of the dots seem to go around this line, there's a lot that's unpredictable about this data. All right, so that's correlation. How do they move together? We can do that statistically by just calculating the correlation, and there's this core function that calculates the correlation between any numeric variables. So here we have the column ROA. Remember, this is data frame temp3, column ROA, data frame temp3, column ROA lead 1, and it will calculate the correlation between them. So here it says 0.68. We can interpret that as a 68% correlation, meaning 1 would be they're perfectly correlated, 0 would be there's no correlation, 68%, that's a fairly high correlation, meaning ROA in 1 year is pretty highly correlated with ROA in the subsequent year. Well, Core can do that for an entire data frame, but it can only do it if these variables are numeric. So if we run this here, it says, oh, this doesn't work because there are some character columns in this data frame. So we could use this select function. This is again part of dplyr. Select means keep only certain columns. So whatever columns you put in here will be the columns that are kept. If you have grouped the data, it'll force the group variable to be in here as well. So that is something to watch out for, but it's ungrouped here, and we are selecting only these columns to look at the correlations. So I create a new data frame temp4, and if I do the correlation on that entire data frame, now we get a correlation matrix. And the correlation matrix says ROA this year, how correlated is it with ROA this year? That's 100% correlation. But ROA this year correlated with ROA next year, 68%. That's what we saw before. And the diagonals give you the same thing here. So 68% here, 68% here. ROA this year is positively correlated with total assets, so about 2% correlation. And it's positively correlated with revenues with about an 8% correlation. So having higher ROA is also correlated with having higher assets and higher revenues. And the same sort of correlation goes when we're looking at ROA for the next year. Higher assets, higher revenues are correlated with higher ROA the next year. Okay, so that gives us some interesting information. As we move forward, we will start to use these correlations and these functions a little more. But one thing we might want to think about is that we have different groups in the data, and those groups might have different correlations. So we will work with some of that here. So you've seen something sort of like this before. I'm going to create an industry variable that is taking SIC, the Standard Industrial Classification Code, starting at the first character, going up to the first character, so it is only using the first character. That's with this substring function. I'm going to create a new industry variable based on that, and I'm going to group by industry. Well, here before we used a mean function. Here I'm going to use the correlation function, which uses the correlation between the ROA column and the ROA lead 1 column. So we will calculate, using the summarize function, the correlation for each industry. So we can run that. Now we haven't gone through what the industry numbers mean, but we can talk a little bit about that. So 1 is forestry and mining, things like that. I think 2 and 3 are manufacturing type industries. 5 and 6 are financials and utilities, things like that. So what do we see? Well, we have one industry where the correlation between ROA 1 year and ROA the next year is really low. We have some others where it is higher, so let's find the highest one. That would be this one. It's a type of manufacturing industry, and the correlation between ROA in 1 year and ROA the next year is quite high. And we have some variation. So this gives us some indication that the data behaves differently across industries. And if we are modeling ROA and trying to predict it in some way, then we may need to consider industries. So what if we don't just have industries? Let's think of some other ways to do it. Here we're going to use the fiscal year. So maybe some years the correlation is higher than others. And we only have a few years here, so We don't see all of the variation that we could see, but let's say 2016, that's the lowest correlation between ROA one year and ROA the next year. 2017 has the highest correlation between ROA one year and ROA the next year. And again, so there could be variation across years in the patterns that are in the data. So here's where we are going to introduce the ranking function. Sometimes we might have other reasons to group companies. So for example, let's say that companies are different by the level of revenue they have. Let's suppose if there's a company with really low revenue, maybe we think that type of company has more or less correlation in their revenues over time, or high levels, that might be the case. So we want to then say which companies are high and which are low according to revenue, so that's what we'll do in this. So again, take temp3, create a new data frame temp4, sort it, group it. By each company, we are going to take the lag of revenues. So the general practice is when you are trying to predict things, you can only use information that comes before the things you're trying to predict. So let's say we're trying to predict the correlation for ROA. We can't use information from time period T or time period T plus 1. So here I'm using the lag of revenue. So we group by GV key, calculate this new revenue, which is the prior year's revenue, group by fiscal year, and rank it. So ranking is going to be done because I've grouped by fiscal year. It's going to rank these companies by revenue for each year, and it's going to group them into 5 groups. So what we should see once we run this is we have high revenue groups and low revenue groups into 5 groups. So let me just run this piece so we can look at that. So this is temp 4. And we look at the last column and we see there are rankings from 1, 2, 4, and 5. So 1, 2, 3, 4, 5 are the revenue rankings here. Another part that we notice here also is there are some missing values in the revenue lag 1. That's because we don't have observations every year. We're going back a year, and then the first year that'll be missing. So we're going to have some things with missing values in here which will cause us some adjustments in what we do next. So then we're going to group by that ranking. So then we want to say for every rank, if you're really high revenue or really low revenue or somewhere in between, what is the correlation between ROA and ROA next year? We've done this already. We're calculating the correlation. I'm going to look at what the median revenue is for each of those groups. So that's the quantile. The median is the 0.5. What we have to do is this na.rm equals true, meaning remove missing values when you calculate the median. And the reason you need that is if you don't do that, then any rank that has a missing value in there will return missing values for this column. So we run all of this and see what it looks like. And after all of that work, right, sometimes it's all the preparation that takes forever. The thing we end up with at the end seems quite simple, but we have ranks. So these were ranked, remember, every year from the lowest 1 to the highest 5. And for each of those groups, we have a correlation. So let's look at the highest. So the highest are for the lowest rank of revenue and the highest rank of revenue. Companies that have really low revenue seem to have high correlations between their ROA one year and their ROA next year. So high or low has that. The lowest are those that have a little bit high revenue. So if you're near the top of the revenue ranking, then your correlation between ROA one year and the next year is the lowest. Here the median revenue just says for each of those groups what was the median. So the median for the low group is 41 million. So we have by company sizes, small companies here. And up here we have some really large companies. So this is 15 billion in assets is the median for this high group. So we've chosen some things by which companies may vary. It might be the case that we think there are groups in the data, but we don't know how to identify those groups. That brings us to clustering algorithms. We will use here what is called k-means clustering. And it's quite simple to do in R, and we can talk about the concepts, but let me just set up how to do it because that's the easiest part. And we need to have a few different variables that we're grouping by. If you cluster by a single thing, then that's the same as like let's say we just clustered by revenue, well, that's the same thing as ranking by revenue, so we don't need to go through the clustering techniques. Here we can cluster by as many columns as we want. I'm just choosing the 4 columns here. I'm going to create them again using the lags. So I'm going to create lag revenue, assets, liabilities, and net income. And then the important part here is when we go to cluster, these clustering algorithms use what is called a distance measure, and if one variable is much larger in size, so for example, if revenues were all in the millions and assets were all in the billions, well, the asset part is going to dominate the clustering that we're doing. So that's why we typically use some sort of standardizing before we do the clustering. So here I'm using the standardizing function. So revenue, assets, liabilities, and net income will look similar across those columns. Then at the end we ungroup and remove missing, because you need to remove missing to do the k-means clustering. We have a new data set that has these new columns, lagged assets, liabilities, net income, and revenues, and we've standardized them. So these are the last columns here, capitals, rev, assets, liabilities, net income, and notice when we standardize them, they're all going to be something like between -1 and +1, something like that here. So we keep only those columns. When we're going to do the clustering, we can only use the numeric columns, so we do that again. And the function is k-means. So it's going to create the distance between different rows, and it's going to try to put rows that are most similar using these columns. It's going to try and put those rows together. So we use this data frame temp. We are going to try and create 5 groups. The challenge with these clustering approaches is you have to tell it how many groups you think there are in the data. There are other ways to go about this, and you might iterate through this and try different things, but you have to tell it here how many columns you want to put in there. So you could try different numbers of groups. Here I'm just using 5. You also have to tell it how many groups to start with, so it's going to randomly assign it to groups. So here I'm telling it randomly assign to 10 different groups, and then from those 10 different groups, take rows and move them between the groups until we get down to 5 groups. So in other words, if we have 10 groups, it keeps moving ones from one of the groups to other groups until it comes up with the smallest distances within the group and the biggest distances across the group. And here sometimes the default won't go long enough to create good groups, so here I'm increasing the maximum number of iterations. It times out at 50 iterations, and you could increase that to as many as it needs to. So I run this, and there's a lot of output that comes with it. I'm just going to highlight a few of these. So if you just put test, it's going to output all of that information. Here I'm just going to output from the TST object, the thing that's sort of like a column, the object centers. It's going to output. It gives us this. So let me tell you what this is. This is the mean from each of the groups that it creates. So we have 5 groups. Those groups have no particular meaning. It's not like an industry. Group 1 is this thing, group 2 is another thing, so because it's just randomly assigning these. So we can look at them and try and get some information about them. So in group 1, this is the mean revenue that came out of that. In group 1, this is the mean assets that came out of that. Similarly, for group 5, this is the mean revenue and the mean assets. So we go through all of these. And remember, these are standardized, so if it's negative, it's lower than the average. So here we have a group that has lower than average revenues, assets, liabilities, and net income. So this is a sort of small company grouping. All of these others are above that group, so it's forced all of these small ones into here. And then these larger ones are all in here, and it varies across the groups. So in this group, let's say this one has the highest revenue. So in group 1, we have really high revenues, pretty high assets, pretty high liabilities, and really high net income. That's this sort of group. Let's find a different one. So here we have pretty high revenues, really high assets, really high liabilities, and pretty high net income. So we're getting an idea that there are different types of groups here. Sometimes this is really important. I'm just trying to get you to understand the possibilities here. So from this TST object, we can pull out which cluster any one of our rows is assigned to. So in temp4, we're going to create a new column, cluster, And how we're going to do that is taking the TST object and pulling in that cluster column. So when we go to temp4 now, you see at the end there is this column that is the cluster column, and it tells which group it has assigned it to. So just as we've done before, we can then do the correlation by each of these clusters, and let's see how they line up. So in the lowest part, so group 4 has the lowest correlation between ROA 1 year and ROA the next year. So let's see what group 4 looked like. Group 4 was the one with really high assets, really high liabilities, and then pretty high revenues and net income. That one, their ROA is not as highly correlated from 1 year to the next. If we look at the highest, that's this group here. So the one with really high correlation between ROA 1 year and ROA the next, that's the group that has really high revenues, really high net income, and pretty low assets and liabilities. What type of company might that be? Well, maybe that's like, I don't know, Amazon or Google or companies like that, that their assets aren't terribly large compared to their company size, but their revenues and net income are really large. We could look in and try and figure out which companies belong to these groups. All right, so we've got some clustering approaches, different ways to group and summarize data. We can summarize all together, we can summarize by group, and some other graphing techniques, as well as some more summarization information. All right, we're getting there. We're starting to develop these skills we can start to use to really analyze the data.